Thanks everyone for coming over to listen to our presentation today. And thank you Black Hat for having us. This is indeed our great pleasure to be here with you. So if you are here, I already assume that you already know what VMware Workstation and Fusion is. So we have been exploring vulnerabilities in VMware and VMware patches for a while now. And the presentation title, The Great Escapes of VMware, kind of summarizes our findings and what all guest-to-host escape attacks we have seen in the recent past. So we have pretty much a lot of content to share with you today and with some demos. So what we'll try to do, we'll try to push the demos to the end of our presentation so that we are good with the timings. So this is about me. My name is Devashish. I'm currently working in McAfee Labs IPS Vulnerability Research team. As a part of the team, my primary job is to find new attacks and provide mitigation for them. And this is my colleague, Yakun, can you please?
Hello, everyone. My name is Yakun Zhang, and I'm also a security researcher from McAfee IPS Vulnerability Research team. I was a malware analyst in the past few years. Now I'm focusing on software and Linux kernel security. You can find me on Twitter. Thank you.
Thanks, Yakun. So this is the agenda of our talk today. We'll quickly start with why we started this research, what was the motivation behind doing this VMware patch analysis that we have been doing for past 1 year. So after that, we are going to quickly jump into the most popular attack surfaces that we have seen that has been targeted by vulnerability researchers to perform guest-to-host escapes. After that, in today's talk, we are going to basically 3 attack surfaces. The first one is the RPC. The second one is the virtual printer attack surface. And after that, we are going to move to the graphics components of VMware. And after that, we'll be finishing our talk with the vulnerability trend analysis of VMware that we have seen and that we may see in the near future. So VM escape is something that scares all of us. If you're someone who is dealing with untrusted code on a daily basis, there cannot be anything more scarier than VM escape. So as you all know that VMware is kind of a sophisticated piece of software. And when it comes to understanding the internals and security implementation of any huge software, beginning is probably always the hardest because you don't have any port of entry. You don't know where to get started from. So we have seen that VMware has been targeted in many exploitation contests in the recent past. And what we have seen after the contest, that most of the details were not even available to public. So the successful exploits were demonstrated, but the details were not public. So our VMware story kind of started in November 2016, when VMware exploitation was exploited twice, I guess, if I'm not wrong, in the Ponfest exploitation contest, and 2 successful exploits were demonstrated. So VMware security actually acted really fast, and they have released patches for those vulnerabilities. So we actually thought probably we can. It was right time to do perform binary diffing and patch diffing to the patches, because if you do binary diffing or patch diffing, so it doesn't only give you a port of entry to a huge software, but it also takes you to the software components that matters the most. And the best thing about post-exploitation contest patches are they will be mostly having security fixes. They are free from any functional or design changes. So we thought probably that was the right time to get started with it. So when we, at the very early stage of our research, what we started doing, we wanted to find out the most popular components of VMware that has been targeted. So we started analyzing the advisory that VMware publishes, and this is what we have come up with. The advisories are mostly not very technical, but it will have some component details, which it was affecting which component. So we have seen some vulnerabilities in SVGA component, which is the graphics of VMware Workstation. And we did see some issues getting fixed in RPC layer. And we have seen some issues getting fixed in virtual printer as well. We did see some other issues, but the numbers were not too much. So in this presentation, we are going to discuss the major one. So we have seen that VMware Workstation and Fusion shares most of the core functionalities. So whenever any patch was applied to Workstation, it was getting applied to Fusion as well. But some of the vulnerability that we are going to demonstrate today were mostly will showcase in Workstation, but they were affecting Fusion as well. So these are, as I have already said, these are the 3 attack surfaces we are going to cover in today's presentation. So we are going to start with the RPC. So the guest operating system and the host operating system has to communicate with each other for a lot of reasons. So if I have to define the VMware RPC in single sentence, it will be like it can be considered as a communication channel that is used by guest operating system and host operating system to communicate with each other. So if you're familiar with VM tools, VMware, you must be familiar with a tool called VM tools that you usually install inside the guest operating system. So this is a tiny piece of software that you install inside the guest operating system, and it makes your life a lot easier by bringing a lot of features like file folder sharing between guest and host, the clipboard sharing, drag and drop, copy paste, and clock synchronization, and there are many features. So most of these features actually need smooth communication between guest and host. So VM tools actually makes use of RPC channel to enable many of these VM tool features in the guest operating system. So once you install VM tools, what you see a new process get started every time the guest boots up. The process name is vmtools.d.exe. So this process is actually responsible for interacting with the RPC channel and do some stuffs that VM tool brings. So when talking about guest RPC mechanism, any application inside the guest operating system willing to communicate with the RPC channel has a couple of options to do that, to communicate. The first option they have is it can directly interact with the VM backdoor. So VM backdoor is a special IO port specific to VMware. We are going to come back to this later on. So the next option it can use the existing APIs that VM tools provide to the application. So VM tools actually comes with a DLL that is known as vmtools.dll. It exports many APIs that you can see here. These are all mostly RPC related APIs. So any application can use this DLL and the exported APIs to communicate with the RPC channel. So now let's talk about the VM backdoor. So VM backdoor can be considered as the lowest component of RPC implementation in VMware, and this is nothing but a special IO port. The set of assembly instruction that you see here, that has to be executed to be able to interact with the VM backdoor. Here the EAX register is holding the VMware magic bytes, and EBX will hold the command number. For guest to host RPC, the command has to be set to hex 1E, and the EBX will hold the parameter required for the command, and EDX will hold the VMware IO port. There are basically two VMware IO ports, 5658 for the low bandwidth, and 5659 is for the high bandwidth communication. And after that, we see a privilege instruction that is called in. So this instruction, when executed inside the guest operating system, the hypervisor kind of hijacks the control flow and process the request accordingly. So this VM backdoor actually supports two protocols. One is RPCI and TCLO. The interesting part about the backdoor is you cannot disable it fully. So it doesn't matter if you have VM tools inside in your guest operating system or not, you cannot disable it fully. So we have talked about some of these features that VM tool bring inside the guest operating system. So to be able to communicate with the host, the guest operating system has to send some command from guest to host. So the guest operating system usually does this by sending RPC packet from guest to host. As you can see here, this is a raw RPC packet we have taken from vmtools.d.exe process. So each and every RPC packet of VMware actually starts with a RPC command string. So when the packet is actually received at the host end, based on this command, the host actually decides how to process the packet. So as you can see here, we are actually sending the process is actually sending VMX tools get version command to the host from guest. So now let's talk about RPC packet handling. So we have come so far that the guest operating system has sent the RPC packet to the host operating system. Now what happens in the host operating system? So if you have a Windows host, for each running virtual machine, you see a process will be there, and the process name is VMware vmx.exe. This process actually holds the most of the virtualization code, the hypervisor code. And since this is pretty complex, it is very attack prone. And this binary will actually handle all these RPC commands that is received from the guest operating system. So since this handles a lot of untrusted data that is coming from the guest operating system, this is considered as the most popular gateway to escape from VMware virtual machines. So to be able to hit those RPC command handler, we somehow should be able to send custom RPC packet from guest to host. As I have already said, there are multiple options to do that, but And what we have seen that the easiest option probably would be to use the existing APIs to send those RPC command. As you can see here, we are using Python C-type library and we are using vmtools.dll to use the existing API to send RPC command. So we are basically using RPC start, RPC send, RPC stop function from vmtools.dll to send RPC packets. So now we are going to take a quick look at some of the vulnerabilities that has been fixed in RPC layer of VMware. So when we started patch analysis, what we have seen that after the Pwn fest was over and we started doing binary diffing, this is what we have come up with. As you can see, the left side, this is a vulnerable code, and VMware has added a fix for this vulnerability by adding a small check. So what is interesting about the vulnerability? What you see here, that there is a memcpy call here, which is highlighted in the red. And the arguments of the memcpy call was actually coming from the second argument that was passed to that function. So when we did some reverse engineering, what we have found that second argument was actually directly coming from the guest operating system, and which is definitely untrusted data. And the data that we are getting as a second argument of the function, it is nothing but a DNDCP RPC packet. And this entire things are untrusted data and coming from host operating system. What we have seen that some of these highlighted structure members, if we can play with that, we can do some interesting stuff using this vulnerability. So after doing some analysis, what you have seen that we can achieve out-of-bound read using that bug. So to be able to achieve an out-of-bound read condition, what you have to do, we have to send an RPC packet with following characteristics. First, we set the packet payload size to maybe for 500 bytes, and we do not put any payload into it. So when the memcpy call will execute, since we have set the payload size to 500, but there is no payload in it, we'll actually overread some data from the next adjacent heap block, and we'll have an out-of-bound read. So the interesting part about this vulnerability was using the same bug, we can achieve out-of-bound overwrite as well. So to be able to achieve out-of-bound overwrite, you have to send more than one packet from guest to host with the following characteristics. Point to be noted here, the session ID of the packet should be the same one. Let's see. So once the first packet is received at the host end, the VMware VMX process will actually allocate a memory in heap of 10,000 bytes, since the binary size is set to 10,000. And since the payload size is set to 500, it will copy 500 bytes of data into the allocated buffer. Now, once the second packet is received at the at the host end, since the session ID is same, VMware VMX will actually use the same allocated buffer to copy the new payload. Since the new payload size is FC00, and we have, if we sum up, we see that we have a 100-byte overwrite, heap overwrite. It will actually overwrite the first few bytes of next adjacent heap block. So this is actually how we can achieve out-of-bound write using the bug. So we have talked about this out-of-bound write. Now, how we can do some interesting stuff using that out-of-bound write. So ASLR is something that has to be bypassed to be able to perform exploitation in modern operating system. So now we are going to take a look how can we bypass ASLR using that out-of-bound write. So to be able to steal info from VMware VMX process, what do we need? We need to prepare a certain memory layout. So this is what you see. This should be the memory layout we need to prepare from in the host operating system to be able to leak some interesting information. So we see we set up the red block that you see. It's the overflow chunk on which we are going to trigger the overflow, and this is the yellow one is the control string which you control from the guest operating system. So the interesting thing about control string is you have from the guest operating system you have access to the read and write to that block, and after that we have a DNDCP object. So once we trigger the overflow, we are going to overwrite some of the initial bytes of the next adjacent heap block, which is the control string. And we do this, and we actually modify the length of the string, the control string. And when the length of the string is modified, and if we try to read back the string from the guest operating system, what we'll have the address of VF table address of DNDCP object in the guest operating system. So once we have the VF-table address of VMware VMX, we can easily craft our find the base address of VMware VMX and craft our rope gadget and perform exploitation. So this was actually it was shown by Chan Security Research Lab. They have published a blog post a few months back, I guess. So we have seen yet another bug that was uncovered in DNDCP. The interesting thing about the bug is this bug is completely identical to the bug we have just discussed. But the only issue is this bug was residing in the DNDCP version 3. So to be able to trigger the vulnerable code, to reach the vulnerable code, from the guest operating system, what attacker has to do, attacker has to downgrade the DNDCP version to 3 from 4. So to be able to do that, you need to simply send following set of RPC command from guest to host. Once the version is downgraded in the host, you can simply perform the exploitation in the same way we have just discussed. So we have seen a use after free issue also got passed in VMware in recent days. So this use after free POC is quite simple. What you have to do, you have to send a certain sequence of RPC command. So first we need to set the DND version to 2 by sending these commands. And after the DND version is set to 2, we need to change the version to re-register the DNDCP version to 3. So once we registered the DNDCP version to 3, the host will actually register version 3 RPC and free some function pointers registered for different version 2 RPCs. The structure actually we have found by reverse engineering that you can see here. So although the function pointers are free, the sum of the associated callbacks that you see here remain active. So that was the problem actually in this issue. So after that, when this scenario, this is the situation in the host process, after that, if you send any of this RPC call from guest operating system to host operating system, we can actually trigger an use after free. So there is an interesting blog that was published recently. We have added the blog into the reference section regarding the exploitation of this bug. So now the question is how these issues could be identified, and now in future, how can we find similar issues in the VMware workstation? So what we can conclude here, we have seen to be able to audit these RPC command handlers, we need basically 4 things. So we need some valid RPC commands, we need some valid RPC packet structure, and any way to send RPC command from guest to host, and some monitoring engine in the host to monitor some of the interesting events that occurred inside the host process. So the valid RPC commands can be easily collected from the open source component of VM tools, and also you can reverse engineer the VMware VMX process to find out this command. And RPC structures are very well defined in the open source component of VM tools. So, and we have already seen how can we send custom RPC packet from guest to host operating system. So we just need to implement a monitoring engine in the host so that we can craft a fuzzer for this RPC command handlers. So we actually have no idea how these bugs were identified, but we think that probably it can be a result of some semi-dumb fuzzing, and and similar issues can be identified if we craft a fuzzer in this way. So now I'd like to request Yakun to explain the virtual printer part.
Okay. The second attack surface we would like to show you is the VMware virtual printer. VMware Virtual Printer is a feature that allows guest virtual machine to print documents by using the available printers on the host. Considering some security reasons, it is not a default feature on the VMware workstation. Users should enable this feature in the VMware Preferences menu before boots the virtual machine. Guest virtual machine uses COM1 port to talk to the virtual print proxy on the host. When user boots a guest virtual machine with virtual printer feature enabled, vprintproxy.exe will be launched on the host by VMware vmx.exe. VMware vmx.exe and vprintproxy.exe are communicated with each other through named pipes. So when user in the guest virtual machine writes data to COM1 port, the data will eventually as an input in vprintproxy.exe. So in this procedure, some operations of EMF spoon file will be processed from the guest to the host. EMF spoon is a meta file format that stores a print job. It contains the device settings and the print content, which is represented by EMF file. We will not go over the details of EMF spoon file in this talk. When vprintproxy.exe receives the print job, it will load tpview.dir to do a print preview work. tpview.dir will pass the EMF content and render the preview on the screen. Because of this interesting function of tpview.dir, one can craft malformed EMF spoon and EMF file, write to COM1 port in the guest virtual machine, trigger bugs in vprintproxy.exe, and finally get the code execution on the host. The architecture is like this. Guest virtual machine writes data to COM1 to VMware VMX.exe on the host. Then VMware VMX.exe will communicate with vprintproxy.exe by named pipes. vprintproxy.exe get the content and load tpview.dll to do the print preview job. After we learn the architecture, we would like to know how to trigger this print preview job by programming. First, we would like to thanks to Google security researcher Kostya. He did a great job on fuzzing tpview.dll vulnerabilities many years ago. Our triggering code is based on his one POC code. In this POC code, the variable div mode contains many preview settings such as the preview page width and height. Variables EMF spoon header and EMRI metafile ext are commonly no need to change. What we should do is preparing a crafted EMF file as the argument of this trigger function. Then it will be fine to do the print job for us. Obviously, this code structure can be easily changed to make a fuzzer as well. Now let me simply explain what is EMF file. EMF is an abbreviation of Enhanced Meta File Format. It's a file format that can store device-independent representations of graphics images. It is very widely used by many softwares, such as the Internet Explorer, Microsoft Office, and some print drivers, including VMware Virtual Printer. Besides the general file header, it is mainly composed of many records named EMR structures. And except the default record types, if you wish to print something like a JPEG file, your JPEG file will be embedded in an EMF file as a customer record. As we mentioned, EMR is the EMF record structure. It contains the properties and definitions for representing the EMF file. EMR has a lot of default types. These types are grouped into many categories, such as bitmap record types, control record types, and so on. For the full details about EMF and EMR structures, you can find the well-documented materials on the Microsoft website. Now let's dive into the issues about the VMware Virtual Printer in these years. VMware Virtual Printer has been regarded as one of the most important attack surfaces in VMware for many years. Early in VMware Workstation 11.1, Kostya of Google security team has found a lot of vulnerabilities in tpview.dll. He has leveraged one Stack Overflow vulnerabilities in tpview.dll JPEG 2000 handling function to a full VMware escape exploit. His exploit code is also used by many other following researchers. In last year, Matus Yuchek fuzzed on the same module based on Kostya's code and discovered 3 CVEs: CVE 2016, 70, 82, 83, and 84. Here, we would like to thanks to Matus Yuchek's great work. VMware also released an advisory VMSA 2016-0014 for these 3 CVEs, so they should already be patched on VMware Workstation version 12.5.0. Next, we will show you the details of these three CVEs and their patch codes for case studies. The first one I want to show you is the CVE 2016-7082. It's a double-free vulnerability in tpview.dl EMR small text out W record handling function. In this function, after some record data passed, the function tried to text out the text in EMR small text out W record. As you could see in the IDA screenshot, at the end of this function, pointer V8 will be free twice. Because the first free is in the else branch, the question is how could we bypass the if branch conditions? Matheus Juchek said, the pointer of A3 at 44 value is always be a non-zero value. So it's difficult to enter the else branch to get the double free triggered. After we did some reverse engineering on the memory, we finally got the achieve method. It's as easily as you just need to add a registry key on the host machine. The registry key you need to add is HK local machine software ThinPrint TPView. And under this key, you also need to add a diva named cliprect and set its value as 0. Then the pointer of A3 at 44 value will be 0. Then the if condition will be bypassed and the double free vulnerability will be triggered. In this WinDebug screenshot, you could see the EDI register is the pointer which would be free twice. Before we called the second free call, the pointer pointed heap buffer was already be freed. Then we invoked the second free call and we got the heap error detected. Now we would like, as we saw at the previous slide, VMware released an advisory VMSA 2016-0014 to fix this CVE. Issue has already been patched. However, the truth is VMware didn't patch it. The picture I show you is a deep patch of the issue function between the VMware Workstation version 12.1.1 and version 12.5.0. You could see there is no any difference between the two versions. Even in the latest version, VMware 14, and the vulnerability still exists. Now we would like to show you a demo about this issue on the latest VMware version 14. Because we can't disclose many details. So we just show a proof of concept of this issue in the latest version of VMware. You could see the version is the latest version 14, VMware 14.0.0. When I run the POC code, you could see the vprint proxy.exe on the host has been crashed. We've already reported this issue to VMware security team, and we think they have already had some solution on this. The second CVE, the CVE 2016-7083, is a memory corruption vulnerability in tpview.dl when handling a malformed TrueType font file embedded EMF spoon file. In this case, in the EMF spoon file, after EMF content, we need to add another structure named EMRI engine font structure. It contains the malformed TrueType font file. tpview.dl will pass the TrueType font file content, get a name table in it, extract the name buffer and name size structure, then call a memsize function to fill the name buffer with name size length 0. This issue is before the memsize call. There is no any security check to restrict the name size. And the name size is in our crafted TrueType font file. It is controlled by us. So if the name size is malformed as a very large number, the process will overwrite the memory with 0 far beyond the name buffer to be an out of bounds write. issue. Now look at the IDA screenshot. Variable v7 is a name size what we could control. Before the main mem side call, there is no any v7 check to ensure its value. In the WinDebug picture, the EDI register is the name size. It is set as a very large number, hex 8F. And then after we call the memset, it made the memory corruption. The patch code added some necessary checks before memset call to mitigate the vulnerability. The last CVE I will show you is the CVE 2016-7084. It's a set of vulnerabilities when tpview.dll decompress the JPEG 2000 file. This CVE includes nearly 40 different crashes discovered by Matus Uchek. From the crashes to know the real reasons of every bug, one should know JPEG 2000 decompression algorithm very much. It's really not a small work for us. In our talk, I'll explain one of them as a case study. It's an out-of-bounds write vulnerability. This out-of-bounds write vulnerability is present in tpview.dll JP2 decompression image function. In this function, it will allocate many buffers to place every decompressed data and also do some data operations on them. Look at the picture. In this function, there is a while loop, takes up the values in a heap buffer, adds some other data, then refuse them to itself. The loop will do the same operation for the whole heap buffer. The heap entry size is hex BO. The filling operation starts from the heap user offset 8. Every value type is a word type. Because hex BO subtracted the heap header and the offset 8 equals to hex AO, it's definitely equals to hex 28 times the word length 4. So the loop times should be hex 28. In programming, we know the loop count variable starts from 0, so the variable should end with hex 27. The problem here is there is no check for the loop times. The while loop will only stop when the decompressed data is consumed. So this issue gives us a chance to do an out-of-bounds write to the next heap entry. In this WinDebug screenshot, the heap buffer is hex 3802AFO. The EDI register is the value the function will add to the buffer value. The EDX register is the loop count, which is already be hex 29. Actually, when it was hex 28, it's already an out-of-bounds write. However, at that time, the EDI register is 0. So after the value added, there is no impact on the memory. But at this time, the EDI register is hex E. The target address is hex 3802B94, which belongs to the next heap buffer header. So after we step over the instruction, the next heap entry header is corrupted. At last, in the patch code, added some safe checks. The loop times could no longer larger than or equal to the proper value. As we saw above, VMware Virtual Printer is so important VMware attack surface. It is very worth to do more parsing work on this. And the EMF file is composed of many complex EMR structures. So it's truly an appropriate parsing target. Thanks to Costia's code, our parsing work is only to mutate the EMR structures and combine them to be a crafted EMI file. Then send the EMI file to virtual printer and wait for capturing a lucky crash. And finally, by this work, well, we've got a couple of interesting issues, and we've already reported them to VMware security team.
Okay, thanks, Yakun. So now we are going to talk about the VMware Workstation graphics components that are susceptible to guest-to-host escape attacks. So we have talked about VM tools before. If you install VM tools in the guest operating system, so along with other component, it also installs a completely fake graphics card. So under Device Manager in any Windows host, it can be seen as VMware SVG 3D device. The special thing about this graphics card is there is no hardware actually exists for this device. So this is a completely fake graphics card. So when the guest has to perform some graphics related operations, the guest has to communicate with this fake device. And to be able to make this communication easier, this fake device actually provides several memory ranges which can be used by the guest OS to communicate with this virtual GPU. So this is a very high-level overview of the VMware SBGA2 device. As you can see, the PCI device can communicate with the host in three medium. The first one is the I/O port. This is a simple in and out instruction that is executed to send some stuff to the host. And the next one is the 2D frame buffer. 2D frame buffer is quite simple. The pixels to be rendered has to be written in this 2D frame buffer, and it will be rendered accordingly. And the last one is the FIFO memory queue. This is quite interesting and complex because to be able to interact with this FIFO memory queue, the guest OS has to write FIFO commands to this FIFO memory queue and wait for the GPU to process the command. Once the command is processed, the GPU will actually execute the command asynchronously and get the result back. So the interesting thing about this FIFO memory queue and this virtual GPU, most of these components are actually implemented in VMware VMX.exe process, which you see in the host, and including the two memory ranges we have talked about, 2D frame buffer and FIFO memory. They are actually directly mapped to the VMware VMX process when any VM is running. So here are some of the example of 2D commands and 3D commands for very obvious reasons. Since the 3D commands are used to do more complex graphic stuffs, the 3D command handlers are more complex than 2D commands. So now if we look at some of the history of the bugs in this FIFO command handling, we'll definitely have to mention the bug that was named as Cloudburst. So this is a very popular bug. The bug was actually present in the 2D command SVGA CMD ret copy, and the command handler did not actually have any check to verify whether the rectangle that is given for copy, it is inside the frame buffer or not. So when the source rectangle is outside the frame buffer and the destination inside the frame buffer, we can actually read arbitrary data from the VMware VMX process into the frame buffer. And we have to remember that the guest frame buffer actually accessible from the host. So once we have the required data inside the frame buffer, we can easily get the data inside the guest operating system. So in this way, we can steal arbitrary information from VMware VMX process. So when the destination is outside the frame buffer and the source is inside the frame buffer, what you can do, we can achieve an arbitrary overwrite as well. So the author has demonstrated how he has achieved a full-fledged guest to host exploit using this abusing this vulnerability. So we have added that in the reference section. If you're interested in details, you can refer to those. So the bug we have just discussed was actually mainly in the FIFO command handler. But when we are analyzing VMware patches in the recent days, what we have noticed that there is a certain shift in the focus. And what we have seen, researchers and vulnerability researchers have shifted their focus to more complex graphics components. For example, graphic shaders. So shaders under VMware are a huge attack surface because of their complexity. So shaders are actually everywhere. Virtually every modern graphics simulation you see in your everyday life in some way powered by codes that is written for the GPU. Starting from the realistic lighting effect in the cutting-edge AAA games to the 2D post-processing effects. A shader can be considered as a program that runs in the graphics pipeline and tells the computer how to render each pixel. So this is mainly used for the shading, applying appropriate level of lights, darkness, and color within an image. So the shader actually can be, in simple word, what we can say, shaders allow graphics developer to directly program the GPU. So this is how the shader input looks like, and after it is compiled and rendered, this is what we get. This is, as you can see, there are some lightning effect, shading effect. So there are two types of shaders, 2D shaders and 3D shaders, and there are two popular graphics libraries available for 2D and 3D graphics rendering. They are OpenGL and Direct3D. Since in this talk we'll be mostly focusing on Windows stuff, whenever we refer to graphics API, we refer to Direct3D. So now let's talk about the life of a shader. So as we already said, the shaders are usually written in HLSL, the high-level shading language, which looks something like this. And in Direct3D version 9, the shaders were actually allowed to be written in intermediate assembly language, but from Direct3D 10, it is mandatory to write the shader in HLSL, which looks something like this. So once the shader is compiled using Direct3D APIs, what we get is shader bytecode. And if you disassemble the shader bytecode using any shader disassembler, what we find is intermediate assembly language. So this intermediate assembly language actually get passed to the GPU driver, and GPU driver will actually convert them to its proprietary instruction, and the GPU will actually execute those instructions. And what we see see some graphics effect in our screen. So now we are going to talk about what if we render a shader inside a VMware workstation. So in the guest OS, when any application use shader, it uses several user mode APIs to process the shader. The shader actually first get compiled, and what we get is shader bytecode. And once the shader is compiled, some VMware specific libraries comes into picture, which actually packs the shader and the shader into SVG 3D command buffer. And the buffer get passed to the kernel mode component of the device, in this case, which is virtual SVG device. And once this is passed, this GPU will, fake GPU will actually pass this 3D command buffer to the host for processing. So once we have received the raw shader bytecode inside this in host operating system, the shader bytecode that we have received at the host, it doesn't necessarily have to be compatible with the host. So the VMware VMX process will have to do some translation, parsing, and conversion to make the shader bytecode compatible with the host operating system. So once this conversion is done and translation is done, and the GPU rendered the process, we see some graphics special effects in the screen. So we have talked about passing 3D command buffer along with shader bytecode from guest to host. Now we are going to see how it is usually done in the guest end. It is done using a protocol that is called SVGA 3D protocol. SVGA 3D protocol is designed to be API vendor and API neutral, but for convenience, it has been designed to be compatible with Direct3D most of the places. So the shader bytecode can be passed from guest to host using a 3D command called SVGA 3D CMD shader define. The parameters to be sent along with this particular 3D commands are defined in a structure which looks something like this, as you can see. So as you can see, the structure holds some characteristics about the shader, which is shader type, and it also holds the raw shader bytecode. So after that, the space for that particular 3D command needs to be, and its parameter needs to be reserved in the FIFO memory queue. So in this example, the function name is SVGA 3D FIFO reserve. It reserves the space for this SVGA 3D FIFO command and arguments. This reservation has to be done by making use of a structure called SVGA 3D CMD header. This header actually looks something like this. And as you can see, this structure actually holds some characteristics about the 3D command that we are going to pass to the GPU to execute. After this reservation is done, what we have to do, we have to simply commit those commands for GPU to be processed and wait for the GPU to finish the execution. So what we have seen so far, we have received the raw shader bytecode in the host operating system. Now, as we have already said, the shader needs to be translated, and the host process actually has to make it compatible with the host GPU. So for that, actually, there are a lot of translation and parsing going on. And you have to remember that when we are actually parsing some untrusted data, there can be some serious issues. So in this screenshot, what you see inside the VMware VMX, it translates each and every guest shader instruction to the host specific shader instruction. The screenshot here shows how the shader opcodes, each opcodes of this intermediate shader assembly get converted. So now we are going to take a quick look some of the vulnerabilities that has been patched in this VMware workstation shaders. So these are some of the advisories that has fixed some shader related issues. We're going to discuss a couple of them. So this is one of the patches that we have noticed when VMware 12.5.5 was released. What you have seen that this particular piece of code are actually responsible for parsing the shader assembly instruction DCL indexable temp. And what we can see here, the argument 2 of this function was actually directly coming from argument 2 was we are writing to this is the heap buffer that we were writing to, and the argument 3 was directly coming from the guest operating system, which is untrusted. So using this bug, actually, we can trigger an arbitrary override. So this is a live debugging screenshot. What you can see here, The destination is RCX, which is the destination heap buffer. It is pointing to heap. And this RD8 actually directly coming from the guest operating system. As you can see, it is set to 4242. So using this bug, actually, we can trigger an arbitrary overwrite, and we can write some data into this heap buffer. Now I'm going to show a quick demo. So this is the vulnerable version of VMware Workstation. This is the POC that we have developed from the patch. So under Windows 10, there is a process called searchui.exe, which actually uses shader to perform some animation. The animation that you see in the start menu, it is usually done using shader. So this process, you will see, will load many of the Direct3D DLLs that are associated with Direct3D. As you can see, some of these DLLs are loaded inside searchui.exe process. Now we have a driver in this place. So before the virtual SVGA device passed the SVGA 3D command buffer to the host operating system, it simply intercepts the content and write our own shader bytecode, custom shader bytecode to be able to trigger the vulnerability. So now when we click on the start button, it should send some SVGA 3D command buffer and along with some shader bytecode to the host operating system. Now when you click on it, as you can see, the VMware Workstation has been crashed. So this is not a zero-day. This vulnerability has already been fixed by VMware. We just developed this POC from the patch. So we have seen a lot of similar issues got patched into the shader parsing code. Here is another issue that has been fixed by VMware. As you can see here, the A2 was the second argument of the function was directly coming from the guest operating system, and it is actually untrusted. And we are writing some content to the certain offset, and we can actually achieve out of bound write using this. And what you can see here, VMware has added a tiny little fix for this, just to make sure that this the argument that is coming from the guest operating system has added some bound checking for that. And there is another issue that has been fixed in shader model 4 DCL intermediate constant buffer parser. As you can see, there is an memcpy call, and the third argument, which is the size of the memcpy, it was directly coming from the host guest operating system. And since this is untrusted data, and we can trigger an out of bound condition here using this memcpy. And VMware has added a fix for this by adding a small check for this, just to make sure that it is not greater than hex 1000. And if it is more than 1000, it will actually take you to some error, and it will just handle the error. So the vulnerabilities we have discussed so far were mostly in the shader model 4. But since, as we have already said, that VMware supports many other operating systems, and the VMware VMX will have other shader model parser code as well. So this is an interesting patch that we have noticed in VMware Workstation. What you can see here, the second argument was actually coming from directly from the guest operating system, and this is the untrusted. VMware actually added this tiny little fix just to make sure that the untrusted data is untrusted. They had added some sanity check on the untrusted data that is coming from the guest operating system. This function actually handles the shader model op call instruction. As you can see, it was directly cross-referenced to that function. This is the actual shader model 1 parser code. Depending on the different assembly instruction, it will redirect. So we have talked about some of the 3 attack surfaces that we have seen attacked most by the vulnerability researcher to perform guest to host escape attack. But what we know that VMware is a very complex piece of software, and there are other components as well. So we predict that we in future we may see some more bugs in the SVGA components as well, because there are many other stuffs, many other this shader assembly parser. So we may see some more bugs in SVGA 2 implementation. And Unity feature is one of the very complex feature that VMware Workstation provides. So we may see some bugs in the Unity feature as well. since this is quite complex, and which bugs may allow to perform guest-to-host escapes. And other than that, every emulated device that we see inside the guest operating system can be susceptible to guest-to-host escape attacks, including the network card, including the sound and everything. So we may see some attacks in the other virtual devices as well. So now this is a takeaways of our talk. As with other softwares, when with the virtualization softwares were developed, probably this guest-to-host escape attacks were not seen as a problem. But guest-to-host escapes are real now. So probably it is the right time to make some changes or security improvement in the core virtualization tools. So we have to, while doing that, we have to keep in mind the attack surface, the overall virtualization security, and definitely the guest-to-host escapes. So in terms of exploitation, what we have seen while reverse engineering VMware Workstation, it lacks a couple of things. Like, for example, there is no CFG protection so far in the VMware VMX process. But we are hopeful that VMware will improve this real soon. So one more suggestion to the virtualization software user would be they should minimize the attack surface by minimizing by detaching the unused or unimportant virtualized components from the virtual machines, which definitely makes the guest-to-host escape more difficult for attackers. So these are some recommended reads that we'd recommend to read if you are interested more about some of these issues. Most of these papers were not published, but it got published in last 1-2 months, I guess. So this brings us to the end of our today's presentation. Thank you guys for your valuable attention, and we'd like to thank the entire IDT research team, and especially Bing Sun. Now we are open to questions. And later also you can send questions to our email addresses. Thanks. Any questions? Yeah.
Thanks for the presentation. Do you have any knowledge about to what extent these vulnerabilities, they also exist in VMware Server?
See, our primary focus was mainly the VMware Workstation. We haven't yet analyzed the VMware servers. But yeah, since this probably it shares some core functionalities, so some of the vulnerabilities maybe we can see in the servers as well. But I have no idea, because our focus was only VMware Workstation. So did I adequately answer your question? Yeah, thanks.
Hello.
Hi.
Very great presentation.
Oh, thanks.
I would like to know, I have saw on one of the slides that the code for the graphical processor generated in the VM, can it be used to execute code on the host machine and to grab the data out of it?
I didn't. Can you repeat once?
The graphical code is generated in the virtual machine itself.
Okay. Yeah. Shader bytecode you were saying, right?
Shader, yeah. Exactly. Can it be used to steal the data from the host machine?
No, see, you are passing the untrusted data to the host operating system, right?
Yes.
So there is no way you can steal data. You can feed arbitrary data to the guest OS, and you may corrupt some memory and do this. But there is no way you can steal data, because it is a one way. You are sending those data from guest to host.
Okay, I understand. But
you got it. But if you are able to trigger some memory corruption into that host process, right, by sending those untrusted data, then you can trigger some. You can steal some information from the process. But this is nothing to do with the shader bytecode. This is a normal exploitation that we have discussed here, right? How to bypass the ASLR and all this. So there is nothing to do with the stealing information, just using the shader bytecode.
Okay, thank you.
Oh, thanks.
What is your claim about the double free bug? Is it a DOS only, or is it more than that? Because the demo was only a crash.
Yakun, the double free crash that you have shown.
Yeah.
I mean, did you get a chance to look into the exploitation?
Look.
The double free bug. You are talking about the use after free in the RPC or the
no, the double free.
Double free.
Double
okay.
free, yeah.
The one.
So what is the claim? Are you claiming is it more than that, or is it just a DOS?
So did you get a chance to check whether it is exploitable or not? No. This is the one in this.
No, that one. Okay, this one.
No, double free, this one. You're talking about this one, right?
That's right. So what is the claim? Is it a DOS bug or is it a exploitable bug?
So I think what we have done so far, we have triggered just to trigger the vulnerable code, and it is just a DOS, but it is definitely exploitable
On Windows?
on Windows, right?
Yeah.
Is it because they're using their own management of heap, or the VMware is using its own management, or is it a Windows management heap?
See, what I feel that since it's a double free issue, right? We need to find a way to create a fake object, right? To be able to exploit this condition. So I think we haven't done any research on this fake object creation. So if you have a way to create a fake object into that freed object inside the freed object, we'll be able to probably gain code execution using that.
No, the only way I'm asking is because double free mitigation on Windows was way past in Windows Service Pack 2 to have a safe unlinking.
Actually,
this is what I'm
the
asking.
matter of the fact is we haven't really get a chance to look into the exploitability of the bug. But the VMware has fixed this issue already, so we are not really quite sure about this. Okay, I think that's it then. Thank you very much, guys. And we'll encourage you to submit feedback. Probably you will get a feedback link in on your registered email address. We'll appreciate that. Thank you very much for your time.